Welcome back. 42 things have changed in this image since the last recording. Can you find them all? All right, we're continuing with Chapter 2, specifically these three topics. And here are the chapter objectives one more time. Operating system design goals can contradict each other, hence there is no perfect operating system design, and in particular the user goal of an easy-to-use system can come into conflict with a system goal of protection and security. Think of a mechanism as a knob that you can turn, and each turn results in a policy, a specific policy. For example, in Linux systems, the administrator can turn on disk quotas and then set those disk quotas to whatever value he or she desires. In Windows, for example, a firewall can be turned on or off, and a specific example, originally in Windows XP the firewall was turned off by default. In, I believe, Service Pack 1 it was turned on by default to provide protection, but at the same time having that firewall turned on made the system a bit more less convenient to use and harder to use for users, non-expert users who may have had to make adjustments to the firewall. The operating system kernel will be written in C or C++ device drivers because they are lower and closer to the hardware. Their lowest pieces may include some bits of assembly language. System daemons, which exist above the kernel, can be written in C, C++, or scripting languages mentioned here, such as Perl, Python. Often they're servers, so any sort of a scripting language that provides networking facilities will do. In the following slides, we'll look at these four operating system structures. DOS's structure is constrained by the simplicity of the original IBM PC. You can see on the left in this figure it appears to be layered, but then there are hooks from the upper layers down to the device drivers and in fact the hardware, so the layering can be circumvented. This is also an artifact of there was no protection whatsoever in DOS. A specific example, the original IBM PC had a maximum 640 kbytes of RAM and often shipped with substantially less RAM than that. UNIX was similarly constrained with a single kernel layer that did everything. Here's a figure illustrating that. Do note that the application program layer cannot directly connect to the hardware layer. So the kernel does provide complete protection to the hardware, unlike MS-DOS's structure. A multi-layered system can provide abstraction and leverage that important concept, as well as provide better protection and security. Disadvantages include a length of call paths. A call from layer N for a service at layer 1 has to pass through all the intervening layers. That will be time consuming because those are all function calls. Another disadvantage or complexity is deciding which services go into which layers, and in such cases dependency cycles have to be avoided. Over time, operating system kernels began to grow large, which resulted in such problems as kernels consuming too much RAM, because kernel code is oftentimes always resident in RAM. Security and protection issues, crash of code running in kernel mode can result in the reboot of the system, whereas code running within a user process will often just result in the termination of that process. And finally, in the early days of multiprocessor systems, there were concurrency problems because early on only one process could be running in kernel mode at a time. So the more kernel code there was, the greater the possibility that a process will be waiting for some other process to leave the kernel so that it could enter the kernel. Hence the rise of microkernels, which sought to move as much kernel code out to user space as possible. So here's an example. Only core functions are executed in kernel mode. Other system functions are executed in user mode. And those services use the kernel layer to communicate via messages, which is a bit of a disadvantage because of the call paths, right? The number of function calls that have to be performed in order to send and receive these messages. There are two approaches to extending the functionality of an operating system. One, assuming you have the source code, is to add that functionality, recompile the kernel, and boot the new kernel. Loadable modules are a second, more flexible approach. They can be inserted and often deleted at will. They don't require recompiling or rebooting the kernel. You'll be writing a loadable module later on this semester. This differs from the microkernel approach in that these modules all execute in kernel mode. In a sense, this approach gives us different flavors of Solaris, which runs on Sun hardware. Oh, and there's a version for PCs as well. No big surprise, but actual operating systems often combine features of many of these organizations. You can see the OS X kernel combines two former operating systems, the Mach microkernel on the left and the traditional UNIX distribution, BSD, which stands for Berkeley Standard Distribution. I'm sorry, that's Berkeley Software Distribution. Interestingly, despite the fact that Apple's mobile devices, in a relative sense, don't have much hardware, iOS is built from OS X. Here are some features of Android. Note that it's a modified Linux kernel written in C, but apps are written in Java and run in the Java virtual machine, which will obviously provide sandboxing capabilities for security and protection. Here's a figure illustrating Android's architecture. Booting a system consists of a number of stages, starting with the execution of BIOS code, which will read the boot disk's master boot record for the next stage boot. There may be a 1.5 stage boot program loaded after that, at which point the next stage could well come from a partition on the boot disk, which will finally load the kernel, and the kernel itself can go through a few stages. Then after all that, the kernel loads up and goes into passive mode after it gets system services started. All right, that concludes Chapter 2. Have you found all 42 things that differ now? Or is it 43?